Hi. Okay. So thank you, Ajit, first for the lovely introduction. uh, as all of you, I'm sure, have heard by now that yesterday at 8:30 p.m. IST, the LIGO Scientific Collaboration and the Virgo Collaboration had a public announcement in which they published the first results from the second observing run. Uh, and one of the major aspects of that announcement was also the announcement of the third discovery, or the detection of a binary black hole coalescence. Uh, we are going to, that's going to be the focus of my talk. And before I start, I should re-emphasize the fact that almost everything that I say here would be on behalf of the LIGO Scientific Collaboration and the Virgo Collaboration. I start with a one-slide summary of what gravitational waves are. Gravitational waves are one of the most interesting predictions of Einstein's theory of general relativity. They are propagating changes of geometry of space-time. They can be thought of as ripples in the fabric of space-time, and they carry energy and angular momentum away from the source. To give you an analogy, just like a time-varying electric dipole moment creates an electromagnetic wave, similarly, a time-varying mass quadrupole moment creates a gravitational wave. When gravitational waves pass through an object, take for example a ring of freely falling particles, it creates a time-varying tidal force. So if you imagine that a gravitational wave is passing perpendicular to the plane of the slide, then this ring of freely falling particles would alternately be stretched in the horizontal or the vertical direction, or along axes that are 45 degrees to the horizontal and the vertical axis. And the polarization of an actual gravitational wave can be a superposition of these two fundamental polarizations. These spacetime states can actually be measured by Michelson interferometers, and that's exactly what you see in this graphic. And you see that the lengths of the arms of the Michelson interferometer stretch or get pulled as a gravitational wave passes through it. This is exactly what we have implemented in the US, which has two 4-kilometer-long Fabry-Perot Michelson interferometers called the Laser Interferometer Gravitational Wave Observatory. They are placed at 2 points in the US that are as far away as possible from each other, in the states of Washington, in Hanford, and in the state of Louisiana at Livingston. The light travel time between these two sites is approximately 10 milliseconds. Now, LIGO is currently working in a setup which is called its advanced version. And the first observing run for Advanced LIGO lasted from 12th September 2015 to the 19th of January 2016, roughly a period of 4 months. And during this observing run, Advanced LIGO detected two highly statistically significant events. One on the 14th of September 2015, which was the first ever direct detection of gravitational waves on Earth. And the second on the 26th of December, Boxing Day, 2015. It had a third, slightly less significant, statistically significant event, which did not qualify as an out-and-out detection, which was on the 12th of October 2015. And this plot essentially shows a summary of all the detections from the entire first observing run. They are plotted both in a chronological order, as well as you can get a hint of the length of the signals keep increasing as you go from top to bottom. The first event was the loudest event that we have detected till now. It was the signal was produced by the coalescence of two stellar mass black holes, which had masses of roughly around 36 and 29 solar masses. But the signal itself was very, very loud. Compared to that, the 26th December Boxing Day event was produced by the coalescence of two black holes that had slightly smaller masses. Also, precisely because of that, the signal lasted a lot more time in our sensitivity region and merged very near the end of our sensitive spot, because of which the portions of the waveform where they merged and the ring down happened, that contained a lot less signal-to-noise ratio. And the signal was more or less dominated by this long period where the two black holes were spiraling in. Oops, sorry. Now, fast forward to November 30th, 2016, and Advanced LIGO, after a break since January 19th, again restarted on its second observing run. And the first results from the second observing run, first results of any kind, got published last night. They are in the form of the letter in PRL, which forms the main text, and is complemented by this supplemental material. This is an actual snapshot of the title of the PRL. So, this is essentially it. On January 4, 2017, at roughly around 3:42 p.m. Indian Standard Time, the two advanced LIGO detectors discovered a gravitational wave signal, which was produced by a binary black hole coalescence. The signal arrived at Hanford first, and 3 milliseconds later, it arrived at Livingston. The network signal-to-noise ratio for this event was calculated to be 13. Just to give you some perspective, the first event was almost double in the signal-to-noise ratio. It was pretty loud. It had a signal-to-noise ratio of 24. But the second event, the Boxing Day event, had a signal-to-noise ratio which was very comparable to the current event, also close to 13. This is what we saw. So the top two panels show the frequency versus the time evolution of the data in the LIGO Hanford detector and in the LIGO Livingston detector. And this has a very characteristic chirpy kind of signature, which is very typical of a binary black hole coalescence. What the third panel shows is the observed data, which is given by the yellow curve, which is the actual strain in the Hanford detector, but only after being bypassed by a bandpass filter to suppress some of the noise artifacts below 30 Hertz and above 350 Hertz. The blue curve shows the strain data of the Livingston detector, but here we have shifted the Livingston data back by 3 milliseconds so that the two strains are exactly on top of one another. The black curve shows the maximum likelihood gravitational waveform that is inferred from parameter estimation. And one would expect that if you subtract out the signal, or what your best estimate of the signal is underlying the data, you would end up with a residual which is consistent with instrumental noise. And almost all the checks that we have done, and actually were done for the first two events as well, and are well in place as far as protocol is concerned, actually showed that that was true. What was the state of the detectors? Oh, we should start this actually. The detectors, if I have to say in one line, were in observation-ready state with sensitivities that were typical of the observing run till date. A slightly more focused view on the the actual plots for the detectors show the amplitude spectral density against frequency for the Hanford detector on the left-hand side plot and the Livingston detector on the right-hand side plot. Now, each of the plots actually have two curves. These are essentially because for each of the detectors, through these plots, we make a comparison between the noise sensitivities during the second observing run to what the noise sensitivity was during the first observing run. So for example, if you look at the left-hand side plot, you find that the yellow curve is the noise sensitivity curve for the current observing run, and the blue curve in the background is what was in the first observing run. Similarly, you see that the Livingston detector also shows an exact comparison between what the sensitivities are now compared to what the sensitivities are or were during the first observing run. Another manual of checks goes into finding whether there is any evidence of instrumental or environmental disturbances that are contributing to a signal. In this particular case, we clearly found that there was none. The searches. How do you dig out a gravitational wave signal from the noise? So what LIGO has currently in place is first an online low latency search or searches. There are several. And then it is followed up by a couple of offline match filtered analysis. What they use is around 5.5 days of coincident data that was collected by both the detectors between the 4th and the 22nd of January 2017. And so what these searches actually do is that they, once you find a signal that appears coincident in both detectors, then you construct some kind of a detection statistic or a ranking statistic that tells you how likely that trigger is to being noise. So if you have a higher value of the detection statistic, it essentially means that that particular candidate is less and less likely to be a noise artifact. So if we are looking for a gravitational wave event, we are ideally looking at the right-hand side of these plots. And you see that there is one event in both these plots, in both these. So I should mention that these two plots are the two offline match filter analysis. So in both these plots, there is one point that is very clearly distinguishable from the noise background, which is given by these black curves. And that was the January 4th event. It had a false alarm rate of less than 1 in 70,000 years. So we are very confident of the statistical significance of this detection. Now, once we have established that we have made a detection, the obvious next step is to try to infer about the properties of the source that gave rise to this signal. And that involves a mechanism and a pipeline called parameter inference. For GW 170104, as with the earlier events as well, we use a Bayesian analysis, a coherent Bayesian analysis of data from both detectors to infer the source parameters. And we use two model waveform families. We did for this particular case, two model waveform families, which are both tuned to numerical relativity simulations with aligned spins, but both had their own approximate prescription to involve or include precession into their system. And one of them did so using an effective single spin parameter describing the precession. That model, henceforth, I will call it as the effective precession model. And one incorporated the complete two-spin dynamics. And that model is called the full precession models. So there are in a series of plots that I'm going to show, after this, including this one, there are going to be some characteristic features. I'll come to this plot in a second. But you will always find these two one-dimensional posteriors that have this red curve, which shows the posterior that is obtained from the full precession model. And there's a blue curve that is not very well visible, but that corresponds to the effective precession model. What we do is combine the posterior samples from both analysis, and we obtain an average posterior. And any two-dimensional posterior that you see here will have two contours, which correspond to the 50% and the 90% credible intervals. So GW170104, we know, was produced by the coalescence of two stellar mass black holes of masses 31 solar masses for the primary black hole and 19 solar masses for the secondary black hole. Here is a comparison of where GW170104 sits with respect to the other detections during the first observing run in LIGO. You would see that it has masses, it has a spread of masses which is somewhere between the LIGO-Virgo trigger and the first detection. Once we have information about the initial masks and the spins, we use some average fits to numerical relativity results to get or to infer the mass and the spin of the final black hole. And the mass of the final black hole in this case was estimated to be somewhere around 49 solar masses, and the final spin was 0.64. Also, for comparison, we give you the estimates that were obtained from the January 4th event with respect to the events that were detected from the first observing run. I should also mention here that these inferences of the mass and spin of the black hole, final black hole from the initial estimates of the masses and spins have had a very significant contribution from members in ICTS. And especially Advanced Ghosh et al., who was a postdoc at ICTS till some time back, and Nathan Johnson McDaniel, who's sitting in the audience. The spins of the black holes play a subdominant role as far as the evolution of the binary is concerned. And hence, they aren't determined as well as we would have hoped for. In fact, the spin magnitudes of the component black holes aren't significantly constrained at all. However, we have certain combinations of the initial spins that are sometimes well constrained. Two such parameters we show here. So we have an effective spin parameter chi effective, which is essentially a mass-weighted combination of the spin components along the direction of the orbital angular momentum, which was estimated pretty well for this event. And if you look at this posterior here, where if you go up along the y-axis, it would mean that it's aligned positively with respect to the orbital angular momentum. And if you go down, it would mean it's anti-aligned with respect to the orbital angular momentum. This has a median value of close to minus 0.12, which suggests a large total spin, which is not positively aligned with the orbital angular momentum. However, as you see, this posterior does not exclude zero spin, so we should keep that in mind. Coming to the other axis, chi p represents a parameter that describes is an effective single parameter that describes the precession in the system. And it goes from a range of 0 to 1, 0 meaning that the system does not have any precession, to 1 where the system has maximum precession. However, the measurement of chi p depends a lot on the measurement of the the components of the spin that are in the plane of the binary, which were not very well estimated. And that got translated to the fact that the chi-p posterior is pretty broad and pretty uninformative, because you see that the green line that represents the prior information that you had when you started the analysis, the posterior is pretty close to that. And which essentially means that we haven't been able to produce any meaningful constraints on precision. Regarding where the source was, at the time of production of GW170104, our median estimates tell us that it was at 880 megaparsec, which kind of, we can make the statement that it's highly likely that it was almost twice as far as the first event. And this was at a redshift of 0.2, approximately. Now, if you look at this plot, the distance estimate comes from a measurement of the amplitude. However, the amplitude of the gravitational wave also depends on the inclination. So this degeneracy leads to a bimodal distribution of the inclination, where you cannot make a very concrete statement whether the binary was facing face on or whether it was face off. So one of the things that gravitational waves from such high mass binaries allow us to do is they allow us to test general relativity in highly relativistic strong field regimes. Something, yeah, sure. Yes. Okay, so if you, so neutron stars have a definite mass range, or something that we know of. Here, if you look at the uncertainties, so these are the 90% uncertainties on this median figure 31.2. And if you take the lowest limit, say 31.2 minus 6 solar masses, that, and same for the secondary black hole, you take the lowest possible limit at the 90%, that is still far greater than what is acceptable for neutron stars. So that's why we know it's not a neutron star binary. Tests of GR, which are allowed, the 4th January event allows us to test it in highly relativistic and strong field regimes. But at this time, what we can also do is sort of combine information that we had already obtained from earlier observations. And that allows us to put some stronger bounds on certain deviations from GR. There were several tests performed on 17004. One of them considered the possibility of a modified dispersion relation and placed bounds on potential deviations from GR. So one added a general additive term to the dispersion relation for a massless particle. And then what you can do is you can, you can put bounds on this prefactor A and the exponent alpha. That is what this plot shows. And on the x-axis are the various values of alpha that were considered. And on the y-axis, it's a bound on the magnitude of the prefactor A. There are two kinds of symbols in this plot. So since we are plotting the magnitude of the A, it can deviate either along the positive a-axis or the negative a-axis. So if our initial assumption of the theory was A greater than 0, those kind of constraints are given by the red symbol, and the blues are for A less than 0. And you'll see that these individual markers themselves are partly filled. So if you take alpha is equal to 1, where the group velocity is exactly same as the speed of light, so anything less than alpha is equal to 1 would mean that you have subluminal propagation. And all the subluminal propagations have, all the subluminal propagations for the red markers have been shown with the lower part of the marker field. Actually, I know there's a lot of information on this plot. The lower part of the marker field, and but for the triangular symbol, you have the upper part of the marker field, and it gets reversed for superluminal propagation for alpha greater than 1. What is important is that these are the first bounds on modified dispersion relations that has ever been gotten from gravitational wave observation. So that's why it's very, very important. Similarly, we have improved our upper bound on the mass of the graviton, and it's consistent with a massless graviton. Another test which was also performed, and this is a test that has also among the first tests of GR performed for the first event, was where you provide tighter constraints on the possible deviations of the post-Newtonian coefficients. Here, these plots actually combine information from all three detections: the first event, the Boxing Day event, and the 4th January event. So we show the constraints, we show the spreads at the individual PN orders by these violin plots, where the predicted value from GR is given by this blue line. I'm not sure whether this is visible very clearly, but there's this blue line that is all along the delta pi is equal to 0 line, which shows you the GR prediction for the deviations. This is the second null test that follows on from the first event itself, and we call that the inspiral merger ring down consistency test. What we do here is we estimate the masses and the spins, or at the mass and the spin of the final remnant black hole object from the initial low frequency part of the waveform and the final high frequency part of the waveform. So if we have a binary black hole waveform in the frequency domain, we consider just the initial part of it that we say corresponds to the inspiral, and we estimate the initial masses and the spins. And then by using some kind of a GR fitting formula, we infer on what the final mass and spin should be. We do the same thing. Sure. So in the this is essentially the plot that showed how you estimate the initial masses. So what you do is you do a Bayesian analysis of the data, where your model is some GR waveform. In this case, we use two model families of GR waveforms, and we sort of for the parameter estimation we do, yes. And this was the information about the spins. So this and this. So it's using the same prescription of a Bayesian analysis, using the same, the model, the waveform models remain same. So for the entire analysis, whatever parameter information that we give are using the same prescription. Mm-hmm. Actually, the frequency evolution was almost identical. It's just that it appears different in the two detectors, because the two signals were actually shown to be coincident, because the way the offline searches work, is that the same template or the same waveform needs to identify the candidate at both detectors. So that's one of the very inherent, like one of the most important subtle properties of the way the searches work. So that's one of the most important things that would let you tell that this is a significant candidate. So there's a time interval, also fixed time interval, within which the same template would have to identify both the signals. So that's how you know that this is a coincident signal. Yeah. Okay. So we have some estimates of the final mass and spin from the initial low frequency part of the waveform. We have an independent estimate of the final mass and spin of the remnant black hole from the final stages of the waveform. What we do is we see whether these estimates are consistent with one another. And because if GR is right, then these estimates should be consistent with one another. Alternatively, what you can do is you can define some fractional parameters in the final mass and some fractional parameters in the final spin, which kind of characterize the relative deviations in these parameters. And so if GR is right, then like consequently, you should expect that these posteriors should be centered around the GR prediction of 0, 0. And this is the corresponding plot for GW 170104, where you see that, so if this is 0, 0, you see that the 50 and the 90% confidence intervals are very well centered around the GR prediction. But we go a step further, and we combine the information that we obtained from this event in particular to the first event. So what we do is the pink contour here gives you the two-dimensional spread in the fractional final mass and the fractional final spin for just the January 4th event. And the blue contour gives you an equivalent spread for the first Monday event. And when you combine these two posteriors, you get a joint posterior given by the dashed black line, which you can see obviously, like it's quite obvious from the plot, that constrains the measurements quite significantly as compared to the two independent measurements that came from the two events. So we were able to obtain tighter bounds on possible deviations from GR. So this was another project that had a lot of contribution from ICTS, as Ajit mentioned in the beginning. What other information do we get from this detection? One is that with this fourth detection, we are in a position to update the information about how frequently binary black holes coalesce in the universe. So we had this number from the first observing run, which was between 9 and 240 events or coalescences per gigaparsec cube per year. And we have been able to squeeze it a bit, and the updated rate after you include the 4th January event in your analysis becomes 12 to 213 coalescences per gigaparsec cube per year. However, when I was mentioning the inferences that we had made from the spins, the information about, I said that it was not very well constrained. However, information about the spins of the component black holes can be very instrumental in giving us some information regarding the astrophysical origins of such binary black hole coalescences. So depending on certain spin measurements to some other kinds of spin measurements, one can actually make statements whether one of the two most favored formation channels for the black holes, whether one dominates over the other. So currently the two favored formation channels for the black holes is that these binary black holes are formed in dynamical capture in dense stellar clusters, or they have evolved in an isolated environment of galactic fields through a common envelope. But given, again, going back to the slide which showed that we were not able to constrain the spin measurements quite a lot, it's very difficult to put a strong statement at this point of time whether one is favored over the other. But at the same time, it actually hints to a very bright future that as we expect more such observations to come in, we will definitely get some light regarding the preference. Sure. So, for example, let's go back to the spin measurements. So you can show that if the independence, the component spins of the two black holes are the tilt angles of the black holes with respect to the orbital angular momentum are isotropically distributed in space, then it would favor dynamical capture in dense stellar clusters. However, if there's a misalignment of the spins, for example, with respect to the orbital angular momentum, and you can conclusively show this in the data, then one can make the inference, obviously, after going through proper models of astrophysical origin, that these have grown through isolated. Oh, sorry, yeah. Yeah, the two are aligned, sorry. Yeah. Then they have gone through a phase of isolated evolution in a galactic field. So here, for example, the chi effective parameter that we measured, that had a negative median, but at the same time, the posterior was wide enough to include zero spins as well. So one, in that case, could not have made, just on the basis of information from that particular observation, about favoring one or the other. Yes. So there are two models that we use to see to predict the distribution of the masses of black holes. So one of the population models uses a power law kind of distribution in the primary mass and assumes that the secondary mass is uniformly distributed within some range. And there's a second model that assumes that, say, the two masses are uniformly are proportional to the logarithms of the masses. These are two distributions that we assume. And then we kind of we constrain the parameters of that model based on the observations that we have had till date. And that then can be extrapolated to these numbers. So what happens is that the two models have their own two ranges, and which are overlapping. But you take the overlapping set. So for example, the minimum number predicted by either of the models to the maximum number predicted by either of the models, and that gives you a sort of an overlapping set that ultimately gets quoted. This is a summary of the paper. Sorry. Yes, yes. So for example, this was the number based on the results of the first observing run. This one, the 9 to 240. You wanted to add something? I should, yes. This is local. Okay, so this is essentially a summary of the paper in itself, and what it essentially says is that the Advanced LIGO, which started its second observing run on the 30th of November 2016, discovered a highly significant gravitational wave signal on the 4th of January. we were able to show that this was produced by the coalescence of two stellar mass black holes with masses and spins comparable to the first event. We make a statement about the spin configurations where both the spins are aligned with the orbital angular momentum being disfavored but not excluded. This 4 January event joins a list of 3 detections, 2 highly statistically significant and 1 slightly less significant event from the first observing run. The general statement that you can make about the predicted rates of binary black hole mergers after this event is that it is consistent with the inferences that we drew from the earlier detections. It also provides an insight into the formation channels of binary black hole mergers. And finally, all the tests of gravity that we performed on it shows that it is consistent with GR. But what? Okay, so now, yeah, sir, yeah. So you use a general dispersion relation. This analysis kind of is parallel to the analysis that goes into the measurement of the graviton mass as well. You just do it for the case where alpha is equal to 0 and A is greater than 0. And you put a bound on the, a lower bound on the Compton graviton wavelength, and that from there you infer a bound on the mass of the graviton. So this comes up as a factor that's added to the phase of the gravitational waveform, and you are essentially putting a bound on possible deviations of that added phase parameter that then you come back and infer about the mass. Yeah, so what are the future prospects? And like we keep saying that it's the dawn of gravitational wave astronomy. So I'm just going to, I'll show you a few slides to actually prove my point that this is not, this is the start of an entire new field. So these were the projected rates for binary black hole detections from Advanced LIGO. And this essentially shows you, along the x-axis, it shows you an increase in the space-time volume relative to the first 16 days of O1. This is actually a result. This is not a new result. This is an old result that was obtained after the first observing run of LIGO. And the first 16 days of O1 is essentially the 16 days of coincident data, which was used to do the analysis for the first event. And you see that as more and more space-time volume becomes available to you, as the reach of the detector becomes higher, bigger, and more massive, you expect your number of detections to increase as well. So bottom line is we are expecting a lot more detections to come in the future. There are a lot of things. Since then? Now the data is being analyzed, we don't know. So the inferences, among the things that are not well known is how these black holes are, what the masses and spin distribution of these black holes are in the universe. So you can get some kind of a picture of how the black hole masses are distributed, say from the parameter estimation for the masses plot, or for that matter, the spins of the estimation of the spins plot. You already see that it kind of does not has a preference towards, or not a preference towards really high spins, or at least these are the 4 spin measurements, or the chi-f measurements that we have made. So all of them seem to be clustered around 0, having a general spread from minus 0.5 to 0.5. This gives us ideas about what, but as more and more detections happen, these distributions and information that lead to these distributions become more and more concrete. It would also allow us to distinguish between different population synthesis models. So there are a lot of models that predict the discovery that describe how binary black holes come into existence. And one such work is currently happening in ICTS and is being led by Sumit Kumar et al. And trying to distinguish between the different population synthesis models. Another question is testing GR. When detections become routine, so what we did for just 2 events, where we combined information from the 2 events to obtain stronger bounds on what possible deviations are possible from GR. As more and more detections come in, we expect these constraints to become narrower and narrower around its GR prediction of 0. This is also work that is being headed at ICTS. Theoretical modeling of gravitational waveforms is one of the most important aspects of gravitational wave astronomy. And the challenges there involve including all relevant physics into gravitational models, some of which are currently missing from them. And this is essentially to prevent us from being biased by systematic errors because of not including certain kinds of information in our gravitational wave models. The examples are, for example, inclusion of information about the subdominant modes, about unknown higher order PN terms. And both Ajit Kumar Mehta and Shashwat Kapadia are 2 members of the AstroRail group who are actively looking into this area of research. One of the most common questions is that you have a lot of exotic compact objects. And how does one distinguish between exotic compact objects, for example, boson stars, Grava stars, from binary black hole coalescences? And one way of doing it is that you put constraints on the properties of such exotic objects, for example, their equation of state, and you derive information whether that can be used to distinguish it from binary black hole coalescences. This is a work that is currently being headed by a couple of projects, one by Nathan Johnson McDaniel at ICTS and another by a former postdoc at ICTS, Arunava Mukherjee. And finally, if you have a lot of gravitational wave detections, it's possible to identify some strongly lensed gravitational wave events and study the properties of the gravitational lens. And this also includes work that is currently being headed by Harris and Ajit Mehta at ICTS. And just to end, I'd say that everything that I presented here is work done by people that are truly spread across the world. So the LIGO-Virgo Collaboration is indeed a world organization, and we are here in that universe. And we are looking towards an extremely exciting future because the gravitational wave sky is slowly filling up. So I'll leave you with the sky map that shows you all the detections, the 3 confident detections and 1 slightly less confident detection that has been detected so far. Thank you.
Yeah. Any questions from the audience?
Yeah, sure.
So in the plot of the 2 masses of the black holes, yeah, that one. So in the combined contour plot, there seems to be, a straight line cutoff for all the detections actually. So does that signify any kind of, what sort of correlation does that signify, or why does that happen?
Oh, that's essentially because the waveform is degenerate in the 2 masses, right? M1 and M2. So you can essentially scan half the parameter space So we put an external cutoff here of M1 being greater than M2, and almost all the information that we have can be constrained to just half.
The contour will be just the reflection of.
Yes. Yes, sure.
So black holes are being formed and they coalesce, so they are also, like the population is dying also, I mean the population becomes smaller and also they are also always being formed. So what kind of density do you use to, like density distribution you said of?
That is actually one of the things that we do not have a lot of information about. For example, the mass distribution and the spin distribution. For example,
over time, cosmic time.
Over cosmic time, I don't think we have very.
Yeah, like they are always getting formed and they coalesce and the population is slowing down. So growth is slowing down. So what kind of models of population density do you follow over time?
For these estimates are actually purely from the observation. It is just the fact that you have observed, n number of events over 1 year or something, and we exactly know our horizon because we know we can compute the distance reach of our detectors very accurately. This is the fact that you're able to see this local universe. It's this many gigaparsec, and we have seen this 4 events per the 6 months of observation time. Gives you a limit of the idea of the event rate. And these numbers are purely from these observations. Even that, you have to assume some mass function of black holes, etc., because our sensitivity is different for different masses. So then that follows some very simple assumptions of various power laws and so on. And you marginalize over all these uncertainties. But how people model these things, there is a big that's a big question, and there are a lot of uncertainties in this. So, one way of you can take some proxies. For example, you can measure the star formation rate at various redshifts. That can be a proxy for the birth rate of black holes also. And similarly, things like supernova rate can be a proxy of the death rate. And so on. So people fold in these models, but these all have large uncertainties. That is why this, this model selection of populations, this models, etc., becomes important because there are all these large number of models that predicts binary black holes, but their at the end properties can be different, which you can infer and you can do the inverse problem. Because from the observed mass distribution, etc., you can try to as time progresses.
Yeah, I read that AstroSat also was somehow part of the news of this. I mean, how the optical observations complement.
So I think AstroSat is an MOU partner now. So what happens is that once a low latency search finds a candidate, you send out alerts to groups of astronomers with which LIGO has memorandum of understanding, so that they can then focus their resources into. So you give them a rough idea of where the event was. So you do at the very preliminary stage, as soon as the candidate is detected, you have although a very big, highly uncertain patch of the sky. You share this information with your electromagnetic partners. And then they can focus their telescopes towards that part of the sky. So for example, for the January 4th event, there were alerts sent to around 30 partners. And they focus their telescopes, which range from gamma rays to radio waves. But this was a black hole coalescence, so it was slightly improbable to expect some electromagnetic counterpart for the coalescence. But to answer your question, yes, AstroSat is someone with which we have a memorandum of understanding. Yes. Counterparts of, yeah. So you were saying, for example, earlier, if there were two neutron stars that collided, then that might have an electromagnetic counterpart, and then people with facilities to detect electromagnetic radiation would be interested in that. Yeah.
So these alerts are sent right?
Yes. Yeah. As soon as possible. Amit wanted to ask something?
There was a very strong prior that you had put on the spin
alignment. Where did that come from?
This one?
Yeah, chi f has, it's a prior which is centered at 0. Where did that come from?
So I think you considered the individual component spins that are, you consider priors on the individual component spins that are uniform in their magnitude and I think have isotropically distributed tilt angles. And this is a derived quantity. So this is essentially the mass-weighted combination of the components of the spins in the direction of the orbital angular momentum. So you kind of fold in the prior on the masses and on the individual spins that finally give you a prior like this.
So this is a prior that takes into account the information of the mass.
I would think so, yes. Because your initial priors are uniform in the component masses, and this is a mass-weighted. I would assume that information gets folded in somewhere as well.
The spins have uniform magnitude between 0 and 1, and they're isotropically distributed. Then if you start with that, or then if you compute this prior on this quantity, that turns out to be like this. So it's a function of mass ratio on the spins.
Yeah, but then again, I think the mass ratio constant also comes from the fact that you have uniform priors on masses, component masses. Yes. Yeah. So you also assume a flat prior. Your masses on the priors on the component masses are flat, and that gives you your corresponding priors or any other mass-derived quantities.
There is a question from someone online, so that how the beep in an interferometer signal gives the idea of black hole mass.
I'm sorry?
How the beep in the interferometer signal gave the idea of black hole mass.
Okay, the beep,
How can you measure the black hole mass from the signal? That is the.
Okay. So I'm guessing the beep refers to the chirp. Okay, so let's go back to the chirp then. Yeah. So this is what I'm guessing he refers to as the beep, because during the first event we had made these sound files that do this whoop kind of chirp, and that essentially spans through increases in the mass. But the actual data looks like something in the third panel, which is the strains as observed from the LIGO Hanford and the LIGO Livingston detectors. And what you do is essentially, this is a really nice representation. This is something that you are doing. So you have different, so you assume a model for GR, and you make the assertion that the signal that is inside this is a GR model. And then you stochastically sample your parameter space to obtain the maximum likelihood, the waveform that is most likely to represent the signal that is hidden in your data. And once you do that, that automatically comes with it, brings with it information about the masses. So that's how, from the bleep, you get the masses. Yeah.
Is there a minimum mass below which you can't ever say for sure that something is happening?
So these searches that take place, they use a sort of bank of waveforms. And they try to see whether one of those templates match with the signal that is hidden in the data. Now these banks of waveforms, we call them template banks. This bank of waveforms are defined, I think, for masses, component masses between 5 solar masses and 100 solar masses. Or I think 5 and 100 to 500, something like that. I'm not sure. Oh, it goes down to 1. So they have limits on the masses. So when you're searching, you actually are searching from a bank of templates. Similarly, there's a spin range as well. So for example, for the offline searches, I think it's 0.0 to 0.99 in magnitude. So yes, so you are looking for certain. Yeah.